Okay, so today we're going to look at nuclear energy. And what we're going to do is we're going to do all of this on our energy diagram. And I think what I'm going to have you guys do is when you turn in your focus sheet, everybody is going to turn in their energy diagram packet. And so what I'll do for each person is you just put it in your focus sheet notebook. And then if you do all of this on your energy diagram, it will count as number 11 of your focus sheet. Okay, so let's talk about nuclear energy. You guys know this from chemistry. Okay, so let's look at nuclear fission. So remember, the goal of all this is to find something that is going to heat water, generate steam, turn a turbine, and generate a flow of electrons. In the previous diagrams, we use coal and natural gas and oil. Now we're going to use atomic energy. So if you look at this nucleus, this is the nucleus of uranium-235. So this is the mass number. And it's a relatively unstable nucleus. So if I bombard it with a neutron, almost like a little bullet, it will cause the nucleus to break into two pieces. And the energy that was holding those pieces together is then released. That energy can be used to heat water, to generate steam, to turn a turbine, and generate a flow of electrons. When you this reaction, however, is not like a chemical reaction, which is sort of a mole to mole, kind of mole of reactant gives mole of product. This is what's called a chain reaction. And it's spontaneous, which means it's not affected by temperature and things like that. So when I bombard this and it breaks apart, more neutrons come out of that. And now I've got 3 more little bullets that can then go find 3 more nuclei. And then I have 9 more bullets that can find 9 nuclei, and so on and so on. The challenge of nuclear energy, one of the greatest challenges, which makes it tricky and can also be one of its greatest concerns, is that this would be a runaway reaction. And that would be that I wouldn't be able to control this. It would keep on going and going and going. And that's basically what an atomic bomb is. We don't want that. So this energy is given off by the uranium-235. That's the fuel that's used. The half-life, by definition, of any of these substances means that over time, as this occurs, I'll have, let's say if I have 10 grams of that substance, after one half-life, I'll have 5. After another half-life, I'll have 2.5, and so on and so on. And so we know how long it would take if we were to let this happen naturally. What we're doing here is pushing it, forcing it to happen faster. Again, we're going to take water, heat into steam, turn a turbine, generate electricity. Now, I'm going to go over all of these things when we look at the diagram, but basically you notice there's the turbine, there's the generator, there's our transmission lines. All of this is going to be the same. It's this part of our diagram that's going to be slightly different. Now, what are some advantages and disadvantages? Nuclear energy is non-renewable because elements like uranium are limited. It's found in the ground. But it doesn't give any combustion products. Basically, the only gas eliminated is water vapor. When you look at what looks like smoke or whatever coming out of a cooling tower of a nuclear power plant, that's water vapor. So it doesn't add all of this NOx and SOx and CO2 in the atmosphere because we're not burning anything. The drawbacks, however, is like meltdown, radioactive contamination, and waste. We still have waste, contaminated radioactive waste sitting on our nuclear sites that we haven't been able to get rid of. But another problem, too, is what's called thermal pollution. Most nuclear power plants are on a river or something like that, because they use enormous amounts of water for cooling. And I'm going to talk about that in a minute. So there is a possibility for thermal pollution. But all in all, the biggest problem we have with all this are all these fuel rods and control rods, that waste, trying to figure out what to do with it. Now, we have had 3 major kind of incidents that you need to know about. 3 Mile Island, Fukushima, Chernobyl. 3 Mile Island was in the United States. Technically, there was just a very small amount of radiation released. It was a partial meltdown during a testing process, but no situation was caused, or no illnesses or deaths were caused. But it did create a lot of fear, because if a nuclear reactor goes too far, then we have something like what we have in Chernobyl. In Chernobyl, we had an explosion, and that explosion put radioactive material into the upper atmosphere and causing a widespread radiation release. So if you look at this map, Chernobyl was here in Ukraine. The radioactive material went all over Europe. In fact, it was atmospheric scientists in Europe that said, we're doing studies, and they were like, why is there radioactive material in the upper atmosphere? Because the government at that time did not tell any of the surrounding countries that this had happened. And these environmental consequences can cause genetic mutations and cancer in people, animals, and plants due to radiation released. We also have contaminated soil and the spread of radiation. Fukushima is still kind of an ongoing problem. It was an earthquake that caused a tsunami, and the tsunami came and triggered cooling pump failure. And we're going to learn that some of the most important things about a nuclear power plant is its ability to cool, because there's so much energy, and that led to a meltdown. And they're still right now trying to figure out how to manage that. All right, so let's look at how a nuclear power plant works, and that will help us understand a little bit more about how these accidents happened. All right, now I'm going to back up with what's familiar, right? This is our reactor, so instead of a furnace, we have what's called a reactor. And this reactor is encased in thick concrete. Remember from your chemistry that radioactivity are particles, and that concrete is one of the best ways in which we can keep even beta particles from penetrating out of that reactor. And so any kind of radiation that's occurring, these small particles and everything, will be contained in this thick concrete reactor. Basically, we're going to take the core, which is where the uranium is, and we're going to put the fuel rods in. And these fuel rods have uranium-235, right? Now up here, put these. So when the neutrons are brought into the fuel, and those nuclei break, remember, we're going to release energy. And this is happening in the water. Water's being circulated all the time. This is going to generate steam. Right? And that steam is going to go into the turbine. Generator. And then the electrons will flow to the transmission lines. Okay, so all in all, it's very similar to a furnace. Now remember, I said that these reactions would be runaway reactions if it's something we're not going to stop it. We can't use temperature or traditional means in which to stop this reaction. So what they do is they use what are called control rods. And these control rods are materials that act like neutron sponges. And if I can lower these control rods into the reactor, let's say it's a really hot day in Texas and I need a lot of electricity, then I keep the control rods out of the reactor for the most part. But if I don't need a lot of electricity and I want to slow the reaction down, I keep the control rods deep into the reactor. So the control rods are how we're going to keep the reaction from running away. Now, this water that's going through here is super hot. Remember, it's going in here. It's causing this to turn. And what we need to do, water's going from here, is we need to cool it. So we're going to send this water in here. This is a cooling tower. We're going to run it down like a shower, down these large, tall cooling towers. And then we can either release it or bring it back to recycle through the process. This pumping of this water is absolutely essential, because if the water is not cooled properly and the water is not being pumped cool, it's going to get hotter and hotter and hotter and hotter. And the reactor is going to get hotter and hotter and hotter and hotter because the water is not cooling it. And this is what can cause a meltdown. These reactors can get so hot that they will literally melt the contents of the reactor. And then you have problems with that. That's really what it scares people the most. Usually, accidents occur in the reactor. And so if anything's going to happen, Fukushima was it circulating, so it wasn't cooling the reactor. In Chernobyl, it was a slightly different design, but they actually had a gas leak and it blew up the whole thing. And then in 3 Mile Island, they had a safety valve that released a little bit of steam and a little bit of radioactive material into the atmosphere. Now, the nice thing about this, though, is that the only thing, that doesn't look very good, does it? The only thing that we are going to release from this is water vapor. And it's non-radioactive because it doesn't come in contact with the actual process. It's just going through cooling. This is non-radioactive water. No greenhouse gases. No pollution. So no NOx, no SOx, any of that stuff. So in this case, what we're doing is we're taking thermal, well, let's start with atomic energy to thermal energy to mechanical energy to electrical energy. In this nuclear power plant. But again, the disadvantages are that we are using a non-renewable resource, which is uranium. This is actually just a UR. Uranium-235. So it's non-renewable, and it does have safety concerns. But the great thing is that it's a pretty straightforward process, and we're not releasing greenhouse gases, no pollution or anything like that. So overall, and with the way that technology has changed, it's interesting. There hasn't been a nuclear power plant built in the United States since like the 1970s and 80s, but there is one being built in Montana that's using a slightly different technology. With the new technologies and the new fuels, because remember too, all of this stuff right here, it's all radioactive. It's waste. All the waste from all nuclear power plants is sitting on site. That's a problem. These new power plants have very limited waste. They're smaller. They're more efficient. Nuclear energy could be something very interesting for our future energy needs.